It's often said that the Sun is a typical star. Indeed, it's the closest star and gives us our most detailed view into how stars work. It's typical in the sense that it's converting hydrogen to helium, which is the job of many stars in the sky and in the Milky Way and in other galaxies. But that's not all that stars do. Other stars are converting heavier elements by the fusion process at higher temperatures in shorter stages of their life, yet other stars are in collapsed or final states of evolution where their states of matter are quite unfamiliar to terrestrial regimes. Every star that gains its energy by fusion, for the time that it is doing that fusion process, is in what's called hydrostatic equilibrium. This is a balance between pressure outwards from the energy released in nuclear reactions and gravity inwards at every point in the star. At every point in the star, that pressure balance is attained, so the star is stable. Stars are not bombs in any sense of the word. We can only make fusion occur in the unstable transient mode of a hydrogen bomb. We haven't yet perfected stable nuclear reactions that might give us fusion energy for our power needs. Stars do this continuously and effortlessly, and are stable for the entire time they're turning hydrogen into helium, as the Sun is. Not only is the Sun stable, and not like a bomb, it's also regulated like a thermostat. If, for some reason, the Sun was compressed by an external agent, such as a nearby dying star, its envelope would be compressed, raising its temperature slightly, which would increase the nuclear reaction rate, pushing back and expanding the envelope. On the other hand, if some process or external event caused the outer envelope of the Sun to expand, it would cool slightly, lowering the nuclear reaction rate and causing the Sun to shrink. In other words, any perturbation in the Sun's properties would lead it to stabilize back at its normal nuclear burning rate. So the Sun is thermostatically regulated to be at its current temperature and to have hydrostatic equilibrium throughout its volume. Stability doesn't, however, mean there are not violent, dynamic, and interesting things going on beneath our gaze and sometimes invisibly below the surface of the Sun. A star like the Sun has different zones of energy transport. The fusion is occurring in the Sun within the central quarter of its radius, or roughly 1/50th of its volume. That's a region within which the temperature is 10 million Kelvin or higher, sufficient for fusion to occur from hydrogen to helium. The very central temperature of the Sun is 15 million Kelvin. That's the fusion burning region. Beyond that is a region where energy travels out through the radiation process, and yet beyond that, energy cannot flow fast enough by radiation, so convective cells are set up in the hot plasma, and the radiation travels to what we see as the surface by convection. Most main sequence stars have radiation zones and convection zones like the Sun. A trick question is, how long does it take energy to get from the core of the Sun to the Earth? Most people think the answer might be 8 minutes. That's the time it takes radiation to get from what we see as the surface or photosphere of the Sun to the Earth, traveling freely through deep space. It turns out that energy generated in the core of the Sun is at a temperature where it emerges as gamma rays. And those gamma rays essentially random walk through the volume of the Sun, colliding frequently with the plasma particles there, particularly electrons, and slowly degrading in temperature and energy as they move out. It actually takes those photons about 150 or 170,000 years to go from the very center of the Sun to its visible edge. Thereafter, it takes only 8 minutes for them to travel to us on the Earth. The visible edge of the Sun is called the photosphere. Looked at in detail, it's a seething mass of small convection turbulent zones carrying energy to the very surface of the Sun. The Sun appears to have a hard edge, but there is no surface. If you send a space probe into the Sun, there would be no bump, no discontinuity. It is a smoothly and continuously varying increase of temperature, density, and pressure as you move through what we see as the Sun's surface. The photosphere, therefore, is just a transition in opacity. Within the photosphere, the density of the plasma is such that a wave of radiation, on average, will meet an electron and scatter. That means that part of the Sun is opaque. The photosphere marks the place where the density thins out to the point where radiation can travel freely. Therefore, traveling in straight lines, we see that as the edge of the Sun. It's quite analogous, although in a different temperature regime, to the surface of a cloud. Flying through a cloud in a plane, we don't feel a hard bump or a severe discontinuity, but there's a clear visible edge. In a cloud in the sky, that visible edge corresponds to a place where the density of water vapor is just a little bit higher than outside the cloud, such that light cannot travel freely, and the cloud is opaque. The edge of the cloud defines the region where the density of water vapor has dropped just enough for light to travel freely, and so we see the edge of the cloud. The violent and dynamic processes of a star like the Sun are not confined to its deep interior, where fusion occurs. The edge of the Sun and regions far beyond the edge also contain energetic phenomena. As radiation leaves the Sun, it heats a surrounding volume to extremely high temperatures, although this is a very thin gas. It's a plasma called the corona, which is heated to a temperature of several million Kelvin. The Sun is also laced by magnetic fields, and many of the surface phenomena and coronal phenomena are associated with changes in the magnetic fields and particle acceleration that occurs in those magnetic fields. Let's look at an animation of the solar dynamo. As was known early in the history of the telescope by Galileo, the Sun is not a solid body and in fact rotates differentially, moving faster at its equator than the pole. The Sun includes a magnetic field, and this differential rotation means that magnetic field is twisted. So the coherent magnetic field the Sun has cannot be maintained, because gradually it's wound up and eventually dissipates. The seed magnetic field then builds and actually switches direction. This cycle, occurring on a 22-year timescale, is the solar cycle, and it corresponds to the magnetic spot cycle as well. The Sun has an overall magnetic field that's like a dipole, like a bar magnet, with a north pole and a south pole, the magnetic field lines extending far into space. But looked up at close, at the surface of the photosphere, the magnetic field where it penetrates the photosphere is marked by sunspots. These are places where loops of magnetic field leave the photosphere and then re-enter. Energy is released from these regions, and it means that sunspots are slightly cooler than the surrounding regions of the photosphere, perhaps 100 degrees cooler, on a base temperature of 5700 Kelvin. The sunspots naturally occur in pairs because they're associated with the threading of the magnetic field in and out of the photosphere. The sunspots also follow the 22-year cycle because they're telltales or external tracers of what's going on with the large-scale coherent magnetic field of the Sun as it winds up, dissipates, and then reforms on that time scale. Although the Sun is stable, slight variations in its energy reaching the surface and moving into deep space can produce dramatic phenomena. Satellites such as NASA's Solar Dynamics Observer have given us exquisite detailed views over time of how these storms penetrate. The most extreme events, coronal ejections, occur when a violent form of sunspot formation ejects loops of magnetic field and high-energy plasma far into space. The size of these storms erupting from the solar surface dwarf the size of the Earth. Coronagraphs are used by ground-based and space-based observatories to blot out the light of the Sun and see the activity of the corona at high energies. This ultraviolet animation shows the enormous range of ejection of material to millions of kilometers from the Sun's surface. This occurs on timescales of days or weeks. If these ejections happen to be pointed at the Earth, it's trouble for us, because those high-energy particles are not shielded completely by the Earth's magnetic field and can cause immediate disruption to our telecommunications activities on Earth. The most extreme version of these events actually cause mayhem. There was one coronal mass ejection in 1965 that took out most of North America's power grid, in particular almost the entire Canadian national grid. No such event has occurred in the last few decades, but it's quite clear that our power systems would not be able to withstand such an event. The radiation, because of the way it interacts and moves through space, does not travel at light speed, so we would actually have a day or so warning of such an event. The heart of the Sun is its fusion core, invisible to us. If we had X-ray eyes, we could see it. And in fact, neutrinos have been observed directly from the solar core where energy is being produced. The mechanism by which the Sun shines and sustains all life on Earth is called the proton-proton chain. It's a three-step nuclear process whereby protons combine in stages to form deuterium, helium-3, and then helium-4, composed of 2 protons and 2 neutrons. At each stage of this process, particles are released, but also radiation, And in the final step, 2 protons are released to partake in future reactions, thereby recycling them. This very efficient process is how the sun gains its energy, and has done for 5 billion years, and will do for nearly another 5 billion years. The best way to think of a star like the sun is a gravity engine. It's gravity that formed the star in the first place. It's gravity that sustains the very high temperatures and pressures that cause nuclear reactions. It's the pressure of gravity in a star's core that causes the electrical repulsion between protons to be overcome such that they can be fused into heavier elements. This requires relativistic speeds within a tiny fraction of the speed of light, for this to happen. In the 3-step fusion chain, helium nuclei are created, so the star is building heavier elements from lighter elements. In the fusion process, the product, a helium nucleus, is slightly lighter than the sum of the particles that made it up. This mass difference, the binding energy, is converted into the radiation that we see. The efficiency of this process in the proton-proton chain is 0.7%. So 1 part in 100, roughly, of the mass energy contained in the nuclei that are being fused is released as radiant energy, sunlight.
The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. The sun is hot, the sun is not a place where we could live, but here on Earth there'd be no life without the light it gives. We need its light, we need its heat, the sunlight that we see. The sunlight comes from our own sun, atomic energy. The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. The sun is hot.
The sun is so hot that everything on it is a gas. Aluminum, copper, iron, and many others.
The sun is large.
If the sun were hollow, a million Earths would fit inside. And yet, it is only a middle-sized star.
The sun is far away.
About 93 million miles away. And that's why it looks so small.
But even when it's out of sight, the sun shines night and day. The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees.
The sun is the one star where we have a ringside seat, and have seen in detail how stars work. It converts hydrogen to helium by the fusion process deep in its core, invisible from our sight, but visible to X-ray telescopes. That radiation slowly diffuses through the sun to reach what's called its photosphere, or its visible surface, at a temperature of only 5,700 Kelvin. The sun has a lot of dynamic activity associated with its magnetic field, which winds up, dissipates, and reforms, associated with places where the magnetic field penetrates the photosphere, which lead to sunspots, and associated with its corona, where in the diffused plasma, extremely high-energy particles are created and accelerating into space. This is the solar wind. We know a lot about the sun and assume that all stars that are converting hydrogen into helium work fundamentally the same way.